Right. Okay, thank you very much. First of all, let me start by thanking the organizers, especially Thomas, who invited me here. It's always a pleasure to come to Vienna. And then thank the brave people who woke up early and came to my talk. So I'm going to talk about sort of some discussions. I mean, we have now for a second year, and this is some project which is finished, some of them which is not finished, some of them in progress. There will be more presumably projects, and you know, we actually don't know some of the, solutions yet. And this is basically a set of problems which one has to rethink something about equivariant cohomology. But anyhow, I will talk about mainly two papers. So one paper, I don't remember, this is on arXiv and actually published. So it's with Nicola Piazzalonga, Nikita Nekrasov, and then Michel Vernier wrote appendix for us. And then there is this paper in progress with Luca Kais and Nicola Piazzalonga. Hopefully it will appear during the fall, and then we have many other discussions with these gentlemen. So let me try to tell you the problem first of all, and then make it more precise. So the problem, and this problem actually propagates, I will describe first classically, and then we will go to quantum setup, is the following. So basically, most of the quantities we calculate in the quantum field theory exact, they're calculated by means of equivariant localization. So typically the idea is the following, that we have some, let's say, tori acting on some manifold, and let's say it's symplectic manifold. And then all our actions, so IVA, are Hamiltonian, right? So they're Hamiltonian. So then quite typically there is this, it has many, I'll ignore them. Okay, I can write it bigger. Okay. IVA omega plus DHA equal to 0. And then there is this theorem which goes, I think, Atiyah-Bott, Bernier, there are many, many names. I even don't remember, but let me call it Atiyah-Bott. And then, or Dusterman-Heckman, I think, presumably better. And then you take omega plus epsilon AHA, right? And you integrate over the manifold, and assuming that the fixed points are isolated, what you do, you are writing something like, this is a sum over fixed points. Then you have to evaluate your Hamiltonians at the fixed points. Okay, and then here typically you have some combinations of epsilons. Let me call them this epsilon. They typically, it's dependent on the fixed data point, but this guy is just a linear combination of those guys, okay? And then typically the whole idea, it's combinatorially very efficient way of calculating things. So basically you just need to know to calculate this integral, you need to know the value of Hamiltonian at fixed point, and then you just need to know how your action looks in neighborhood of fixed points. So you need to read these weights. And the whole thing is that if you concentrate on compact manifolds, right? So what you know for compact manifold that, if you put epsilons to 0, so if you take epsilon equal to 0 on the left-hand side, then you would just basically have omega in some whatever dimensions here. So this will be a good integral. And then from that side, you just have to expand on omega. So first of all, on compact manifold, you know this would be regular, and this will be just some number. But important thing that what you know that basically we'll have this geometrical integral plus terms of order of epsilon for compact. So this is for compact. It's just some power. So it's dimensions, complex dimensions of your manifold, let's say. Okay, so if you want, so it's a complex dimensions of your manifold. So you calculate symplectic volume, and of course it's very efficient and has been a lot of works, etc. Now the problem is what we realized. The problem is what do we do? What do we do for non-compact? Because for non-compact, this argument fails because you cannot set epsilons to 0. This integral is not well defined. And a priori, what you will have, the structure of the answer you will have would be the following. So for non-compact, so typically if you choose your Hamiltonians appropriately, this will be a well-defined integral because actually Hamiltonian magically will force you to decay at infinity. And then what you will have some very singular terms in epsilon. Typically, again, it's a dimensions complex of the manifold symbolically. Then less singular terms, then there will be terms of basically some zeros order of an epsilon and something like this, right? So you can just, for example, treat this function, as a rational expand this, etc. But then once you go to complicated examples, for example, one of the things is that you don't know how to extract the information, what's going on, what does it mean non-equivariant limit, which information is invariant, etc. So that's what we were facing at some point. This is a problem. So let me try to make it more precise, and then I will tell you actually this type of problems. I mean, they're classical, but then they will propagate. I will tell you something about Gromov-Witten invariance and stuff like this, okay? It's mess, I mean, a priori. So if you take a complicated enough examples, it will be mess. I will write for you 2 examples. So I'm not a complicated person. I will write examples. I mean, I will not give you a general theory. Sorry? About dots, it's a higher order, so right? Roughly speaking, what will happen if you expand on these things? So these things will look like, I mean, the orders. So this looks like you have expansion of epsilon t k, k from 0 to infinity symbolically, whatever, 1 over k factorial. And then here you have epsilon complex dimension of the manifold. And then you can, for example, start to expand the things. Sorry. So I will tend to write small, I think, but I will try to be my best. So symbolically, it's like this, right? And then this is epsilon dimensions of the manifold complex. So then, a priori, you will see in examples it's a complicated thing because if you have many torus sections, I mean, you can decide how you expand, etc. But it's definitely a function not regular around epsilon 0. So this is different. This is functions regulate epsilon 0. This, I don't know, whatever. You have to discuss it. And then you can decide how to expand these terms. You will see an example. Sometimes what is important, it's even hard to define what's order of 0 in epsilon, what's not. Again, we are trying to expand around 0, but when there are too many epsilons, it becomes messy. I'm just trying to indicate for you the problem. And then we have to understand, are there any meanings in these coefficients, etc. So let's get more concrete because, of course, I need to build more technology for doing this more meaningful. And of course, I will look basically at Kahler quotients or Kahler toric manifolds. Toric manifolds. So what's data do I have? So I have a Cn there. And of course, on this Cn, I have action of Tn tori, which rotate things, obviously. So let me pick up some sub-tori Tr in Tn, and then I will specify how this guy is embedded by what people typically call just charge matrix in physics. Charge matrix. Which if you want, so I will tell you that I will have this moment maps. I will have moment maps mu A is equal sum of q a I from 1 to n, and then I will have coefficient zeta I square. Right, so this is my moment map, and coefficient A runs from 1 to r. Z just complex coordinates on my Cn, okay? So this is what I'm doing. I pick up the things, and again, typically you would say that I would have a Kahler quotient. I don't know, let me call it xt. It depends on choice of t, which would be basically I have to go to 0 to this fixed level of moment maps, and then I quotient by this u1s r. And again, in principle, you have to be aware it's complicated things. So to avoid orbifolds, you have to put certain coprime conditions on this charge matrix. And also, actually, this manifold depends on the values of t. This is what's called chamber structure, so you have to choose it. But in principle, this is what you are doing, okay? And then, for example, in this story, we would like to discuss all these issues. And so how do you calculate, the volumes here, for example? Let's start from the volume and then discuss cohomology. So let me define my volume in the following way. So I will call epsilon t. So, and then you can write the following very clever formula, I think, which is originally was given by Witten, and then people like Jeffrey and Kiron actually proved mathematically this, but the formula is the following. So let me write, first of all, 2n zeta integral over Cn, okay? And then, again, I will introduce epsilons, but I will introduce epsilons for whole tori. So I will have, of course, they're redundant. When I'm doing quotients, I will have much smaller torus section here, but I can keep track of all these epsilons, which is in this guy. And then I can write something like this, minus I from 1 to n, epsilon I zeta I square. So if I write this thing, this is what would be just the current volume of, of my Cn. But then what I will do here, I will also put A from 1 to R, and I will put the delta functions for my moment map. The Q is hiding in definitions of moment map, right? So again, what I'm doing is I'm taking integral on Cn, right? And then I put a delta function there. So delta function forces me to go to this level. But because this guy is invariant under U1, up to U1 factors, this is just up to some whatever 2 pi factors, it just collapses to the volume of the space. So this is supposed to be a volume of my space. And the thing is now, I mean, if you don't have this term, if everything compact, this would be a volume. So this is, for example, a very efficient way of calculating the volume of Pn if you want. Otherwise, of course, this is a equivariant upgrade. And you can see if your space is non-compact, then you have to keep these guys to be well defined. Okay? So, and so from this point of view, it's obvious what to do. But then what you can do in this integral more, you can actually take this function and then these things, and then you can, this part, write as a product of whatever d phi a from 1 to r, and then you just write I phi a, now Thomas will complain, qa I zeta I square minus ti. So I'm just writing for you integral representation of this delta function. And what Witten figured out, but again, in Witten's case, he did something more complicated, but then again, mathematicians actually did it better. Then, of course, if you do this integration over phi, you get delta function, and this is by definition volume, but what you can decide, you can do other way around. So you integrate over zeta, and integration over zeta, this is basically a Gaussian integration. So if you do it, then what you will get the following. So I will just, so when you have to change, so typically people put here 2 pi a from y, e by a t a, and then you would have a product I from 1 to n, epsilon I plus ui a phi a. So this integral you can do, I mean, right away. This is very trivial integral because the angles variables goes away, and this is just doing very trivial integral. Of course, the whole thing is here, and this is where the main headache to prove that this makes sense. You have to pick up a clever contour, because then you will reduce your problem to calculating these residual integrals, and that's, so this contour, it's a tricky thing to analyze, but this is, again, that's when it was made a theorem. This goes under Jeffrey-Kirwan prescription. Again, Jeffrey-Kirwan prescription, it's a simple prescription in terms of sort of meaning, because what you have to do, if you take simple enough example with phi integration, you basically have to see, you have to choose what your values of epsilon, your t, And then when you do integrations, you have to close the contour depending on convergence. Either you close, I mean, like this or like this, and depending, some poles goes under the contour, some outside, etc. Of course, when you have multiple integrations, it becomes incredibly complicated. But again, actually, convergence of integral is driving the things. But Jeffrey Kirwan actually gave a purely algorithmic description, etc. So that's what object we want to study. And let me do example right away. Okay. So the most stupid example we can do is P1. Okay. So P1, this is just a C2, and my charge matrix would be 1, 1, right? So my moment map will be zeta 1 square plus zeta 2 square equal to T. Okay. And then here, so this integral, which I will get over epsilon T. So if I just read the thing, this would be this whatever d phi 2 pi I e phi t. And then I will just have a epsilon 1 plus phi, epsilon 2 plus phi. And then if you do this calculation, I mean, this is not a hard calculation, will be get epsilon 1 t, epsilon 2 minus epsilon 1 plus minus epsilon 2 t, epsilon 1 minus epsilon 2. And you can observe right away that peculiarity of this guy is the following, that see, okay, so this guy, you have to take two poles, both. Yeah, of course I can draw. So depending, so the poles will be here. So the pole will be minus epsilon 1, minus epsilon 2, and then you do this contour. But what I want to observe to you that, I mean, this is by construction, this is a volume of P1, so this will start from T plus terms of order of epsilon. This is how it's organized by definition, okay? So now let's discuss a bit the meaning of this integral and which objects appear in here and what's going on here. So you actually doing some evaluations, but you can not necessarily put here phi t, you can put any functions of t, or phi, sorry. So actually, I can think of any functions of phi and epsilon as elements of cohomology. So my equivariant cohomology can be thought as following. I just take C, it's a polynomials phi, epsilon 1, epsilon 2, and then I quotient by these relations, which is given by poles. So the integral implements you these things right away, okay? But in principle, this is a equivariant cohomology. So at the level of ring structure, I can take any object like this, and then I have to quotient by these two things. So by the way, as you can see, doing a non-equivariant limits at the level of ring structure, this is very trivial. I mean, if I send my epsilon psi to 0, I mean, I just get this, which is usual de Rham cohomology. Okay, so now let me just tell you some trivial things. So in principle, what I can do, I can take any function of P1, yeah. When you take, I mean, volume form, and so and the square of the volume form is 0. So right. So it's degree 2. Yeah. Okay. So then what I'm doing is, so if I take some function of phi or possibly epsilons, then I can evaluate this guy. So I'm writing this d phi with these things, okay? So I'm taking element in cohomology, then I'm evaluating, and I get something, and this is something would be, I don't know, some number plus terms of order of epsilon. There are no troubles. And in this picture, what I can do, I can play with cohomology here. I can, I don't know, go to non-equivariant limits, and then I can evaluate this integral, and I get this number. And this is all basically original things. What I'm doing, I'm just calculating this original geometrical integral. Okay, there are no troubles. And of course, you can keep going and you can write cohomology. And basically, it's a very efficient way of describing cohomology. So if you know these Jeffrey-Kirwan things, you know which poles to take, and then you can keep going. So of course, it's a trivial example, but the complexity combinatorial grows up very fast. Okay, so again, I'm stressing to you, everything here is perfect, and I don't have to, so doing these things or doing these things is the same stuff, and I can put epsilons to 0 whenever way I want, yes? Well, I just expand an epsilon. What I'm trying to tell you that the first term will vanish, right? Right. So, well, whatever coefficients, I mean, I don't know. You just expand the things. What I'm trying to say, it's regular in epsilon. There are no problems and epsilon's equal to 0, right? So I can basically, in these expressions, I can put epsilons to 0 consistently, and I get some, right. So, I mean, I'm very sloppy with the factors, maybe 2 pi's, etc. But this is basically a very efficient way of calculating. I mean, this is some exercise how to calculate the volumes of Pn. Okay, good. So everything is good, but let's just go to some different case and then try to realize the problem. Okay. So the next example to me would be is the following one. So this would be O minus 2 over P1. So this is actually a cotangent bundle of P1. So for those who love geometry, it's just resolutions of C2 over by zeta 2. So then from point of Kahler geometry, my charge matrix will be this one, 1, 1, minus 2. Yeah, sure. I will come to quantum cohomology, wait. I mean, it's a classical equivariant cohomology, and there is usual cohomology. There is no quantum cohomology so far. Sorry, I'm not following, I mean, your question, so I cannot answer since I don't understand. We can discuss later privately. Okay, it's a second attempt, unsuccessful. So, I mean, I will come to quantum cohomology if I have time. So let me do this example. So this is a O minus 2 bundle over P1. So the moment map is zeta 1 square plus zeta 2 square minus 2 zeta 3 square equal to T. O minus 2 bundle over, I don't know, P1. It's a line bundle over, I mean, it's a line bundle, yeah. It's a standard notation. Okay, no, but just think it's a line bundle, or if you want to think the most simplest way, just accept the fact that it's a way of constructing cotangent bundle over P1. So there is someone proved the theorem that if you want to construct cotangent bundle over P1, which is obviously non-compact, you can just do this Kahler quotient with these things. So, I mean, of course, it's not trivial fact to show that this is the same, but if you go to local coordinates, do patching, I mean, you can show. So just accept this fact. But for you, it's obvious that this is non-compact space. This is my main issue. So then what I'm doing these things, and then I have to write for you this object, okay? So if you do this object, f of t, then I will get d phi over 2 pi I. So I will have here phi t, and then I will have epsilon 1 plus phi, epsilon 2 plus phi, epsilon 3 minus 2 phi. And this corresponding the contour actually would be the same. So the only thing what's going on that, I mean, the pole here, I mean, this will pole have a different sign. So Jeffrey-Kirwan pole, so if you want, so there will be pole here, which would be whatever epsilon 3 over 2, and they will be pole minus epsilon 1 minus epsilon 2, and the contour will be the same. Okay, so again, it's a math theorem. It's proven by this person's Jeffrey Kirwan in 90s. So then if I do the thing, so let me tell you right away. So what you get minus epsilon t, then you will get here epsilon 2 minus epsilon 1, then I get epsilon 3 plus 2 epsilon 1 plus e minus epsilon 2t, epsilon 1 minus epsilon 2, epsilon 3 plus 2 epsilon 2. So you can see already that, okay, nothing I can do. I mean, here, this would have singular terms, whatever I'm trying to do. So even if I start to play with epsilons, I will have a singular terms. So now let's discuss cohomology here in this example. Right. So my main message is that whatever I did there, I will have some troubles, and I have to address how I'm dealing with these troubles. So if I look at cohomology now, so the cohomology of this guy will be, from one side, very similar to P of cotangent bundle of P1, equivariant cohomology. Right. So my equivariant cohomology now will be C, function of phi, epsilon 1, epsilon 2, epsilon 3. And I will quotient still by phi plus epsilon 1, phi plus epsilon 2. Right. Right. But you see, there is this idea is that, and here it's actually when you start to do concrete calculations, goes bizarre thing, because typically the integration is supposed to be it's a map from equivariant cohomology to cohomology of the point, and the cohomology of the point, it's typically whatever, it's Taylor in epsilon, etc. This doesn't work in non-compact case, so I mean this doesn't work. And so here what you can see that if I look at this integral, so I perform explicitly integral, and of course, I cannot set epsilons to 0, or I have to come with some prescription or whatever. So basically what's going on with this integral, I can take my element of cohomology, but if I believe this Jeffrey Kirwan prescription, okay, I have to be very careful because generically these guys will have terms which start from 1 over epsilon, some power plus, etc. So it's basically a singular guy. And so, unlike compact manifolds, I cannot manipulate now with cohomology with this map. I can go to ring structure. So again, the thing is that this is, in a moment, I will discuss for Giventhal functions, and I will tell you where is Giventhal gets in trouble, because at cohomology level, it's very easy to take non-equivalent limits. But if you start to integrate, then on non-compact guys, you have troubles. For compact guys, there are no troubles, but for non-compact guys, there are troubles. So that was a problem we realized, and then again, let me just make another comment here. So this is what's important I forgot to make. So you can describe this cohomology this way, or you can think also another way of thinking about this. So this is very important for further applications. So let me give you this for the sphere first. So either I'm talking about this, so this is some stuff which vanishes on the integral, but I could equivalently write for you basically PDE or ODE in this case for these guys. So ODE is the following, it's O1 plus dt, epsilon 2 plus dt, acting on f of epsilon t, this is equal to 0. T, it's derivative in respect to moment map. So you see what I'm doing, I'm telling you that the integral, if I do this insertions of these guys, this is trivially 0. But I can take these insertions and I can generalize these insertions by acting derivatives. So I can think about my equivariant cohomology, either I'm dealing with some differential operators or I'm dealing with this stuff. Okay, so this is, I will tend to call, so I will write these differential operators quite often di ui d dta. So this operator is associated to compact divisors, but what I'm trying to tell you now, if you look at this example, for example, here the equivariant cohomology is exactly the same, well, as an operator. So it's just usual derivative. Okay. So now you can take here non-equivariant limit very easily, because what I'm telling you, I'm not telling you anything genius. I'm just telling you that second derivative of t, f of epsilon t is equal to 0. So you know it's a linear function, and that's exactly what I got. Okay. Of course, the same logic doesn't work simply because if I'm not restricting myself to a regular solution, so if I don't have any regularity in epsilon, I mean, it doesn't make sense. Okay. So this is the issue. So let me try to, first of all, tell you roughly how we resolved this in first paper. And again, I will give you conceptual, and then I will switch to quantum cohomology and tell you how this propagates there. So the issue is the following, that in principle, when you look at these two examples, which is very trivial, of course, examples, and you know, this you can do by hands. The main thing that actually you can ask by which problem and this coefficient, this expansion, are they controlled? So if you can start to expand in epsilons, other things are controlling by some way. And actually they are controlling if you observe the following stuff. So if you take this integral, if you look at the contour integral, and you will act by this operator, which I call d3 of f of epsilon t, which is basically the following operator, epsilon 3 minus d minus 2 dt f of epsilon t, then you can see this removes this last guy, and this last guy exactly which differentiates between cotangent bundle of P1 and P1. So what I do know that if d3 of phi epsilon t acts on this, this actually becomes regular at epsilon equal to 0. Again, it's a very trivial example, but if you put these two guys, that actually tells you quite a lot, because now this is what's called in toric geometry, this is called compact divisor. So in principle, you can look at this problem. So you have your manifold, and so you have your quotient Cn U1R. And then you can see, so the compact divisors, it's basically if you're in original things, you take a moment map and you put one of zeta i's to 0 and see what's going on to the quotient. Then this guy you call divisor, it's a toric divisor. So you take a moment map conditions and you have to go through all the zetas and see. And there are sometimes in non-compact examples, some of these guys are compact, and this is called compact divisors. And compact divisors actually one-to-one correspondence with a compact cohomology. So this is paper with Nekrasov and appendix by Vernier, so this is what we call shift equation. I will, you wanna, this one, okay, yep. Is it okay? Okay, so the idea is the following, that basically you can study, so this formula has a structure. So you have these relations, but then you would have a bunch of compact divisors, and this compact divisors with cohomologies going on. So remember that one of the interpretation of the value of moment maps, this is, you can think as just coordinates in a cohomology. Because one of the ways quite often is to derive them, for example, in the physics literature, is you integrate over some cycles and you write this TA. So these guys actually are related to parameterizations of H2 of DRAM in the toric cases. Toric divisors related to compact cohomology, and a priori compactly supported cohomology is not part. I mean, they related to each other rather tricky way, but what you do have is the following. You have the all H2. Oh, yeah, but I'm discussing only toric. No. Of course. No, I'm discussing toric case. Otherwise, this issue becomes not very manageable. You don't have enough info. So everything I'm saying, it's a toric case. So then you have H2 compact, and then you have action on H2 DRAM to H2 DRAM. So this is written in this book by Both 2. So what you take compactly supported form, you take a form, and you can map omega plus omega compact. But there is no any canonical way to say that compactly supported cohomology is part of DRAM cohomology. So algebraically, on all these examples, you actually can figure out what's the action of compact cohomology. And again, because of toric examples, it's related. So there is this map from compact to HDRAM. But I cannot say that, HDRAM decomposes something compact plus the rest canonically. Right. Which, it requires I have to choose non-canonically. This map, this is a map that I can map from compact cohomology elements to DRAM. This actually goes through Poincare duality. So Poincare duality on non-compact manifolds has both, certain cycle has both, Poincare dual in a compact cohomology and in DRAM cohomology. So these actually facts, a very basic fact, but typically most of the people don't, if they don't look at this exotic subject, they don't know. But it's in both 2 books even written, I think, all this stuff. So there are these 2 maps. And as Anton said, the main problem is that I cannot intuitively, and this is what some physicists tend to think, is that you can think of DRAM as a compact plus the rest. Non-normalizable modes or whatever, but this is formally wrong. You cannot do it in any canonical way. But anyhow, what you can do, you can figure out exactly how this cohomology acts in a toric case, and what you will get the following equations: phi of epsilon t minus, so there is some, let me write mi, f of epsilon t plus psi m. So m is just redundant things, but basically what I'm saying to you, that think that t, and this is just exactly compact cohomology act. So I have to figure out at the level of the basis how these guys act on this. So this is a part of Q matrix related to compact divisors. So there is a theorem that compact divisors one-to-one with basis elements of compact cohomology. So if you do the thing, then this becomes regular. So you can actually calculate PTM plus terms of order of epsilon. So this is regular. And this is invariant data. It's some map. I'm not. No psi exponent, yeah. This is, let me make one comment. I would hope that Vernier will solve it. Because actually this section should be properly defined in the level of equivariant cohomology. So in principle, if you look at mass literature, there exists, equivariant cohomology, and there exists equivariant cohomology with the coefficients compactly supported. It's very hard to define it. So, but one thing should act on another thing. So I haven't seen this explicitly written or whatever, but this is basically the part of the things we have to discuss. So, we know this coefficient sort of experimental and, No, right. But what I'm saying, my question is the following. So if I don't know, give you some cohomology, which we have very good algebraic descriptions, I don't know, functions, polynomials, phi and epsilon quotient by this. If you ask me how to describe analogously, equivariant cohomology for compacts, I have no clue. Formally, it should exist. Formally, it should act. And this is our hope that mathematicians, can do it. So, in a way, what we understand this intuitively, what we are doing. We can prove the theorem. We know that this is related to the section. But of course, I would expect that eventually math people should do it more properly. So it's actions of different equivariant cohomologies. Okay. And then the thing is that why this equation is nice, it basically tells you which information is finite, which is not. Psi is just some map. So, so this is a QAIMI, where I runs through all compact divisors. If there are no compact divisors, there is refinement of the statement. You will get second order difference equation. It's a Q, but I have to prove for you that in principle, you have to go through geometry to prove that the action in this basis, the action of compactly supported cohomology on DRAM is given by this matrix. So I'm skipping it. But conceptually, I'm telling you, I have some coordinates on DRAM. If I figure out how in this basis my compactly supported cohomology acts, then what I'm doing, conceptually, I'm doing something very simple. If you think it's, so I'm taking omega dimensions of the manifold minus omega plus omega compact dimensions of the manifold, and this would be a regular well-defined. The only problem is that what I'm writing to you, this is intuitive, the picture, but I cannot make it precise. This is intuition, but otherwise it's nonsense. Because this object is not well-defined. But you see it's organized in such a way that the top terms just canceled out. So this, yeah. The leading term, which is divergent, just cancel out. And all other guys will have a compactly supported, so it will put them on a compact manifold. Of course, the main thing that this formula intuitively very clear, but you cannot write as a mathematical statement. You have to go to all the equivalent things, etc. So in principle, this is the information you can write, and this is a way of deducing, but the main trouble becomes is that when, and this is, for example, examples when you read it. So in simple examples, so even cotangent bundle, for example, my coefficient there will be, this of order of epsilon will be actually in some way unique. But once I start to have examples when there is a big gaps between H2 and H2 compact, I will get a lot of ambiguities. And these ambiguities actually propagate in the intersection numbers, etc. And people without realizing, for example, in string theory literature, actually for different Calabi-Yaus use different intersection polynomials without knowing. And in both cases, it worked. And actually, it's related by, these two things are related by blindness to this action of compact cohomology. Okay. So again, let me make one comment, however, for hungry mathematicians. So again, we are physicists, we observe fact, we understood how to calculate things. And so Michel wrote appendix in more math forms, but I think it's sort of formula as a theory, maybe it's not satisfactory. And in principle, when you go to higher cohomologies, for example, let me tell you, there is a conifold, resolved conifold. H2 compact is empty, but H4 compact is not empty. So we know that we can write the second order difference equation, and we can prove it. And we can do it for other examples, but I don't know what physically, what it means there, because it's like H4 compact acts on H2. So I have no clue. So there is this sort of open problems which we don't know. So we know the result, but we don't know how to understand it better. Okay, good. So now let's do something better. Of course, when you have this, cohomology, so let's start from P1. And again, P1 is a boring case, but it's sort of technically simple enough. So as I told you, we can look at this object. So we have this operator. Right? And I can say that this is my, whatever I call it, equivariant volume. Then there exists a natural deformation, and this deformation actually related to Gromov-Witten's story. So what I can do, there exists a quantum equivariant cohomology. So it will be basically this PD, ODE in this case. Minus lambda t. So lambda is a new parameter. So when I send lambda to infinity, I go to original things. Otherwise, I will get this. So this is called, this is relations for quantum equivariant cohomology. And of course, here, if you take a limit epsilons to 0, which you can do in this case, you will get this equation. So let me have this epsilon. So this is 0. This is actually a famous Pickard-Fuchs equation. And of course, Pickard-Fuchs equation is just deformation of this equation. So D, I introduced new object. So I had F. D, it stands for the disk, actually. Right, I changed the equation. So I deformed these equations, but when I send lambda to infinity, it collapses to this equation. Okay, so these relations typically, because you recognize what I'm doing, right? So I'm saying now phi square equal to some constant element. So this is quantum cohomology. This is a equivariant upgrade of this thing. So I can say D1, D2 equal to some constant element. It's a quantum equivariant cohomology. I mean, at that level, I'm not saying anything genius besides what Giventhal said more than 20 years ago, okay? But here in this example, what you can see is the idea is the following. So you can pose the question as the following, for example, mathematically. You would like to find the solutions of this equation in such a way that semi-classically it collapses to some element. So you specify equivariant element of cohomology, whatever you want, and then you get something and you get the things. And for example, if you specify this element of cohomology clever, for example, there is, let me not go there, but if you put here gamma class and you deform the things, you can reproduce Gromov-Witten invariants for P1. Okay. But there are no problems with doing epsilons. And also, let me tell you, just give you the idea what's going on. So, for example, you can ask how FD is written. If you wish, this is some alternative definition what Giventhal was writing 20 years ago. Because what I can tell you is the following, that if I'm thinking about this guy, so I can write for you this F disk. So let me skip lambda just to put it to 1, not to carry around. But F disk I can write to you as the same Jeffrey-Kirwan integral. And then I will write to you this guy, epsilon phi t. And then here I will have a F phi epsilon 1 plus phi epsilon 2 plus phi. And I would like that this object, so I'm just introducing to you this integral kernel, and I would not say that this guy solved this equation. So this is a equivariant Giventhal I function. Yep. If lambda is not 1, I will have some powers here, lambda of here. I can write to you later on, and it just, lambda is important that if you want to be very pedantic, it's important thing that when you take lambda to infinity, I want to go to original element. So this guy is constructed in such a way that when I send my lambda to infinity, I just collapse to usual classical cohomology. So this is formal object. So let me write to you that you just get idea. These formulas, for example, you can find in Giventhal things. So this is E phi t plus, just to give you idea, N1 infinity E minus NT phi t. Then here L from 1 to N, L plus minus phi plus epsilon 1, s from 1 to n, s minus phi plus epsilon 2. So it's constructed the way that it solved that question. So actually, to construct given tile function is that, I mean, you can just write this equation equivalently. You can actually construct formula in terms of operators because basically, and then you can just recast in this form, etc. So this done is, again, this is definition. So now the main thing that given tile define this object defined on cohomology. And for example, at the level of ring structure or problem, so for example, you can set epsilons to 0, and then you can expand these guys up to whatever cohomology. So you have 0, phi t, and then you would have some whatever constant terms plus term of phi, some complicated functions, and terms phi 2 you can ignore. And that's a Gromov-Witten invariant, genus 0 Gromov-Witten invariance for P1. Okay. But again, let me stress to you the things that you can play these games, and of course it gets complicated, but for compact examples, I can have the write this function, I can put the integral, I can evaluate, I can set epsilons to 0 either before or after I deduce a correct coefficient, there are no troubles. Okay. It does depend on lambda. I just dropped it because the formulas will be very messy if I start to put, of course it does depend on lambda. But lambda actually, the scaling in lambda, you can go to coordinates when scaling in lambda and in phi is very related. So in given tile language, this is what's he called H bar. Sorry, not, yeah, it's just conventions. I don't go, I just don't want to write complicated formulas, that's the only thing. But of course, you know, philosophically, I have to have a deformation parameter. Then you understand that I'm deforming classical problem to something quantum. So lambda, it's a parameter which deform cohomology. So now you can anticipate that if I try to do, so I don't have much time, but if I try to do the same things in, so here, what is important, if you start to play this game, which is very trivial, and I think in papers like from end of 90s, for example, given tile did all PN cases, so all projective spaces. And again, there you don't, I mean, you can do it equivariantly, non-equivariantly, but all the things you can read these coefficients, and if you evaluate the integrals, I mean, things will be either way the same. Now, you already can smell the problem for non-compact cases. And these problems actually becomes not bad problems and very bad problems. And of course, this part given tile did not discuss. So in principle, I can go to other examples. So for example, I can go to this example which I discussed to you. And then here the correct quantum cohomology equation would be the following one. So this would be epsilon 1 plus dt, epsilon 2 plus dt, minus, again, I forgot this lambda, then I will have 1 plus epsilon 3 minus 2 dt. It's a quantum cohomology relation for cotangent bundle. No, it did. Thomas, everything depends on lambda. I just don't drop a lambda. I can write formulas with lambda. So lambda will be here, lambda will be here, etc. Right? Yeah, I'm just dropping it for the sake of simply writing formulas. Okay. So this is quantum cohomology for cotangent bundle. So the trouble, for example, you can anticipate right away. I mean, it's trouble or not, you have to study. But the thing is that, of course, so this equation is very famous for this example. If you look at many old papers by Yao, I mean, I think this example is very famous to get Gromov-Witten. So this is a baby version of this example. But now if you think from equivariant cohomology, if you can put epsilons to 0 or not, it depends what you want to require from solution. If you want your solution start, for example, from an equivariant volume, you have no right to put epsilons to 0 here, right? Because if solutions is singular in epsilon, then a priori, you know, you cannot do it. But of course, in mirror symmetry problem is that people go back and forth, etc. Of course, here FD, you can write exactly formally the same way. So the given Thal function here will be the same thing. The only thing I have to add here will be epsilon 3 minus 2 phi. And then these guys will have extra things. So I'm writing now for another example. So this would be now k from 0 to 2n minus 1. Just a moment, 2, 5. I'm telling you the following fact, that you give me these equations, and this equation can be uniquely solved if you specify semiclassics. Okay. We want, so, okay, in physics, people say that if you fix correctly semiclassics, you get some function, and this function, upon certain sort of manipulation, encodes all genus 0 Gromov Witten. Okay? No, of course, but you know, the genius of Giventhal was saying is you do the things, you do something which you can put on a computer, gives you numbers, okay? And what I'm trying to say that his genius methods 100% works for compact cases. For non-compact cases, there are troubles, and there are different degrees of troubles, okay? And actually, people 20 years ago already saw this trouble. They thought that they're simply stupid, but I mean, there are some tables which Clem and Yao were writing, and they were getting half-integer Gopakumar-Waff invariants, and they thought they're wrong. I mean, this is actually exactly problems in the same corners we cannot get equivariant. So there is something is going on. What exactly is going on? This is another question. But in principle, you can think, I mean, the problem is the following. What we can do, we have this equivariant cohomology, and then, for example, we can try to deform it. So I definitely don't have time, but for example, there is another very nice deformation. It's with H bar. So I can write for you k-theoretical things. So instead of calculating the volume, I can calculate certain equivariant sections of the things, and this will be H bar deformation. And for example, this H bar deformation will be satisfied just, you know, exponential version of these guys, etc. So there are this deformation. You can also make k-theoretical deformation here. So we are looking what's a natural deformation there, etc. But what is important that we have this integrals evaluating, okay? And then we have to decide how to deduce this information. The Giventhal is telling you that you just construct this object, put epsilons to 0 in cohomology, in equivariant cohomology, expand individual cohomology, read coefficients. For example, they will be a solution of Pickard-Fuchs, okay? I'm now telling you this cannot be true in general, a priori, right? Because if I just think about this, if I'm writing for you these things, the only thing that this will be a solution of usual Pickard-Fuchs equations if this is regular in epsilon. But who told me that I have to pick up a regular in epsilon? I mean, they can be, I mean, there are millions of solutions which don't have to be regular in epsilons. And actually, this is physically relevant. So this is the name of the game, okay? So what I'm trying to tell you that if I go to more complicated examples, I actually start to have problems. So this evaluation, going in cohomology to 0, evaluation, etc., this sort of does not commute. There are a lot of troubles. And there are different troubles. For example, this problem, and this is what people actually saw in the literature, a lot of things are not actually problematic, and they're not problematic because here instantons very easily have non-equivariant things. And this is actually happens to this equation. So if you stare here, this is a classical part. So this is classical, D1, D2. But here it's another operator, but this is all compact divisors. So this guy, and this guy are compact divisors. So if you look at Giventhal function here, you have a first term, classical term, and you have these guys. But now just stare at this, guys. This is a compact divisor, and it starts from 0. So it means that in cohomology, it removes all stuff automatically. So everything works. And this is what many people, did many examples. Basically, they don't care how to switch things. But you see, the magic is that this works. You can go, for example, to other classical example. This is my main advice, that if you go to mirror symmetry book, there are whatever, 2, 3 examples, and everyone calculates the same. Local P2, local P1 times P1, etc. This is all bad examples. In a way, they are very classical. You go to local F2, you're in trouble. So instantons start to blow up because the structure of given tile function does not have a compact divisor here. So basically, there are these 2 examples. There are examples which is very nice when you deform classical homology, but in deformations, you always present compact divisor. So it means that when you construct these towers of things, you will get compact divisor acting there, and it guarantees you that everything is well defined. But there are examples when you, go to local F2 manifold, it's not true anymore. And then basically one tower of instantons get a trouble. So, we are doing this way, etc. But then we go to given tile, Yao, Zaslav, and I don't remember who, from the end of 90s, and they were doing this from Pickard, Fuchs, etc. And then they have these columns and a few examples when they write 1/2, they put a question mark, they said we don't know what to do. Again, I don't know what's the deep relation between what I'm saying and what those guys are saying, but they had troubles. Either mirror symmetry doesn't work, or, I don't know. Nekrasov claims there is no problem on A model, or there is mirror symmetry, but I'm just saying there are a priori some ways when you don't know how to manipulate this given tile function. Not always, but there is somewhere. So I think, as always, I had more to say, but my message is actually, I wanted to tell you the thing. So of course, my intention was also tell you something combinatorial, about this K-theoretical, because all the story has K-theoretical lived. So there are a lot of fun stuff there, etc. But the main thing that what I'm telling you, that you also have to manipulate here with the shift equations, etc. And for example, there is this also wrong perception for non-compact manifold that if you know intersection numbers and you look at Pickard-Fuchs, it constructs you everywhere. Actually, what we realize, depending on examples, you don't need to know exact intersection numbers because that's not uniquely defined, but still Gromov-Witten invariants can be defined, etc. So this is basically an example when it's good to look at old problems, and actually my main advice is, guys, do examples, don't prove theorems. Do examples, because here we actually, for half year, we wanted to prove a theorem that every instanton is finite before we hit it F2 example, which is wrong. So it's definitely, so examples are very good. Okay, I think I will stop here. Sorry for overrunning time.